Okay, so we are in sections 5.1 and 5.2, and again, we are talking about shear stress from torsion. So we've developed our equation that shear stress equals T rho over J. And if we're wanting the maximum, then we use the entire radius, so TC over J. J is our polar moment of inertia. And if it is solid, it is pi over 2 c to the fourth. And if it is not solid, if it's hollow, it's c outer to the fourth minus c inner to the fourth. And remember, c is radius. Okay, so we have a shaft that's made from an aluminum alloy having an allowable shear stress of 100 megapascals. So we have an allowable of 100 times 10 to the sixth pascals, which remember a pascal is a Newton per meter squared. If the diameter of the shaft is 100 millimeters, then I know that the radius is 50 millimeters, which is 0.05 meters. Okay. Determine the maximum torque that can be transmitted. What would the maximum torque be if a 75 millimeter diameter hole were bored? Okay, so let's first start with this one. So shear stress equals TC over J for our maximum. And we have 100 times 10 to the 6th pascals, which is a Newton per meter squared, equals, we don't know that torque. Okay, our radius is 0.05 meters. And our polar moment of inertia is pi over 2 times 0.05 meters to the fourth. So we can calculate through that our shear stress, that the maximum value of our torque that we can have is going to be 100 e to the sixth, enter, pi is a number, 2 divided by 0.05, enter, to the fourth, times 0.05 divided by. And so my torque can be, that's in newtons, so 1, 2, 3, so 19.6 kilonewtons. That would be the maximum torque we can have if it's solid. Okay, now it says, well, what would it be if we bored a hole? Well, I know that if we bore a hole, then we're going to go from a diameter of 100, okay, and we have an internal radius of 50. So let's just kind of look at this. So I have a radius of 50 millimeters, which is 0.05 meters, and I want to bore a hole. And when I look at that hole, it is a diameter of 75 millimeters. So 75 divided by 2 is 37.5 millimeters. Divide that by 1,000 to get it into meters. And so I'm going to have this internal radius of 0.0375 meters. Okay. So now I'm going to have to use my polar moment of inertia for hollow. So it's going to be the same shear stress. So I have 100 times 10 to the 6th newtons per meter squared equals my allowable torque. The maximum shear stress still occurs at the outside, okay, at the outside edge of my cross section, pi over 2, and then I'm going to have 0.05 to the fourth minus, okay, minus 0.0375 to the fourth. And this time we calculate the torque. I'm going to have 100 e to the sixth. Pi is a number, 2 divided by 0.05, enter, to the fourth, 0.0375, enter, to the fourth, minus, times, and then divided by 0.05, which is my radius. Okay, this time the maximum torque that I get is 13,422 newtons. So 1, 2, 3, 13.4 kilonewtons. 13.4 kilonewtons. Okay, so that would be the maximum. And now it says sketch the shear stress distribution. Well, what is our shear stress distribution going to be? We calculated that the maximum for our hollow, we put it at 100 megapascals. So if I'm looking at this twist, okay, it is going to be coming down, and we're coming down, we're coming down, we're coming down. And this value right here, this maximum stress, is equal to 100 megapascals because that's what we designed it for. Okay, when I look over here, okay, again, it's going to dotted line in here, come across. We're going to come down on the outside to a maximum stress, because that's what we designed it for, to 100 megapascals. But now we have to actually find this internal amount because it's now hollow. So how would I find this internal part? Well, I know that shear stress, okay, equals T rho over J, and this time our torque was 13.4 times 10 to the third. That's in newtons. The outside, oh, we don't want the outside. We need that inside. So this time it's 0.035 meters because we have to use that internal radius. And then again, it's still the same polar moment of inertia of 0.05 to the fourth minus 0.0375 to the fourth. Okay, so let's calculate that stress. So I have 13.4 times 10 to the third. There we have it, 0.035 times. Pi as a number, 2 divided by 0.05 enter to the fourth, 0.0375 enter to the fourth, minus times and divided by. And 1, 2, 3, 4, 5, 6. I get 69. We're just going to call that 70, but let's just make sure. So I should have 13.4, okay, times 0.0375 times, okay, and then we have pi as a number, 4 divided by 0.05 enter, whoops, to the fourth, 0.0375 enter to the fourth, minus times divided by. And I get a different number because of course I do. 13.4 e to the third, enter. 0.0375, that should be a 0.0375. 0.0375 times pi as a number, 2 divided by 0.05 enter to the fourth, 0.0375 enter to the fourth, minus times divided by. Okay. 1, 2, 3, 4, 5, 6. So 74.8 megapascals. So that's what this value is right here. That's going to be 74.8 megapascals. Okay, there you have it.